In this video, we'll combine our different spectroscopic techniques and different pieces of data to arrive at a full structure of a molecule. And often when you're given multiple pieces of data, it can be hard to know how to combine the information to arrive at a reasonable structure. It can be difficult to know where to start. So that's what we'll look at in this video. And my recommendation is to follow the sequence of steps outlined here. And this video will walk you through each step in more detail. First, if you're given the molecular formula, then determine the unsaturation number. And we've seen this before, so this will serve as a review. We have two ways to determine the unsaturation number. First, from a structure. And in a structure, the unsaturation number is the number of rings plus the number of pi bonds. In the first example here, we have 1 ring and 3 pi bonds, so the unsaturation number is 4. We can also use the formula. And if that makes more sense for you, by just plugging in the number of carbons, 6, and the number of hydrogens, 6, we arrive at the same answer. In the second example, the triple bond is 2 pi bonds, and so we have an unsaturation number of 2. In the third case, we have 1 ring and 1 pi bond, so again, the unsaturation number is 2. We can also determine the unsaturation number from the molecular formula when we're not given a structure. And here we need to use the formula in the gray box. So in the first case, we have 4 carbons and 2 hydrogens. The oxygens don't factor into the formula because they don't change the number of hydrogens that will be present in the structure. This gives an unsaturation number of 4. In the second example, we take 7 carbons times 2 plus 2, and then subtract the number of hydrogens, 9, and the number of chlorines, 1, and then divide by 2. That gives us 3 as our degree of unsaturation. In the final example, remember that we add the number of nitrogens, so we will have 2 times 4 plus 2 plus 1, the number of nitrogens. Then we subtract the 9 hydrogens and divide by 2 to get an unsaturation number of 1. Sometimes you won't be given a structure or a formula, but instead you'll be given the elemental analysis data, or the percent composition of carbon, hydrogen, and nitrogen. In these cases, you'll need to determine the formula, and there are 2 ways that we'll do this. First is the case in which you've been given the mass or the molecular weight of the molecule. In this case, to determine the number of carbons you have, you'll multiply that mass by the fraction of carbon divided by 12, the mass of carbon. Similarly, to determine the number of hydrogens you have, you'll multiply the mass by the fraction of hydrogen. Then you'll assume that the remainder of your mass is oxygen, unless you're told otherwise. And you'll multiply the mass by the fraction of oxygen divided by 16, the mass of oxygen. Let's take a look at this example. We're told that the mass is 302.189. So to determine the number of carbons in the formula, I'll multiply 302.189 by the fraction of carbon, 0.754, divided by 12, the mass of carbon. This gives me 18.99 carbons. I follow the same sequence of steps for the hydrogen and the oxygen, and I find 26.29 hydrogens and 3.00 oxygens. This gives me a formula of C19H26O3. If you're not given the molecular weight of the compound, then instead of multiplying by the mass, which you don't have, you'll divide the values by the smallest result. For example, if we're given only the percentage of carbon and hydrogen, then we'll divide each of those percentages through by the mass of that atom. So using our same example, 75.4 divided by 12, and 8.7 divided by 1. Assume oxygen is the remainder of the mass, and then divide through by 16. This gives us 6.28, 8.7, and 0.99. Because these aren't integer values, we'll multiply through by 3 in this case to arrive at integer values, giving us a formula of C19H26O3. Then with our formula, we return to step 1 and determine the unsaturation number. Once we've determined the unsaturation number, we should look at the IR spectrum and identify any characteristic functional groups. In particular, I recommend looking for carbonyl groups, double or triple bonds, and OH or NH stretches. In this spectrum, for example, the only key functional group is really a carbonyl stretch here at 1737 wave numbers. But we can also identify our typical CH stretches around 3000 wave numbers. Next, I'll look at the carbon-13 NMR spectrum. And although we haven't formally been introduced to these spectra yet, we can use them in their simplest form, and that's to determine how many kinds of carbon the structure has. Here the rules of symmetry function just as they do for proton NMR spectroscopy, and so the number of signals in a carbon NMR spectrum will tell us how many kinds of carbon we have. One step beyond that, we can use the three regions listed here to distinguish aliphatic, or sp3 hybridized carbons, olefin or aromatic carbons, sp2 hybridized carbons, and carbonyl compounds, which appear in their own region downfield between 160 and 210 ppm. So in this particular spectrum, we have 6 different carbons. The peak at 77 is the solvent, so we need to ignore that one. And then of the 6 remaining, 3 of them are in the aliphatic region, or arise from sp3 hybridized carbons. 2 are in the alkene, or aromatic region, and 1 is a carbonyl compound. And already with that very superficial analysis of the carbon-13 NMR spectrum, we can propose a structure that's consistent with the spectrum. I need to include a carbonyl and an alkene, and then 3 alkyl carbons. And so a structure like the one I've drawn here is consistent with the spectrum. Then I recommend tackling the proton NMR spectrum last. And this is an in-depth analysis that has 3 components. First, you'll use the integration. You'll determine the number of protons in the structure and compare it to the number of carbons. Then you'll look at the chemical shift values to determine the kinds of functional groups in your structure and compare them to what you determined from the IR spectrum. Then you'll analyze the coupling patterns. You'll draw partial structures from each of your peaks and use the multiplicities to help you piece them together in the right order. In the spectrum shown here, the integrations are on the bottom and tell us that as we move from left to right across the spectrum, the peaks arise from 2 hydrogens, 3 hydrogens, and 3 hydrogens. The chemical shift value at 1 ppm tells us that this group is near only aliphatic or alkyl groups, while the peak at 2.0 and the peak at 2.4 are next to an X group, like a carbonyl or a halide. Then we analyze the multiplicity. Starting with the most upfield peak, this is a triplet, which means it's next to 2 hydrogens, or a CH2 group. So I can draw a partial structure that's a CH3 bound to a CH2. I'll bold the CH3 to remind myself that those are the protons giving rise to the signal, and the CH2 protons are simply next to it, or indicated by the splitting. The peak at 2.1 ppm is a singlet, which means it's next to no neighboring protons. The integration of 3 hydrogens tells us that it's a methyl group, and so here I can draw a partial structure that's a methyl group bound to an X group, something electron withdrawing with no protons on it. The last peak is a quartet, meaning that it's next to 3 other hydrogens. The integration of 2 tells me that it's a CH2 group, and the multiplicity tells me it's next to a CH3 group. The chemical shift tells me it's also next to an X group, so I can draw this partial structure where the CH2 is between a carbonyl and a methyl group. Then I can put these pieces together by finding my 2 ends, the 2 methyl groups, and then putting the CH2 in the middle. And now this coupling information helps me do that, because the coupling told me that the CH2 is next to a methyl, and the coupling told me that the methyl is next to a CH2 group. So I end up with a final structure shown here, methyl ethyl ketone. Now usually once you get to a structure, you'll want to stop, but I strongly encourage you to check your structure to make sure it's reasonable. And that's because there's often multiple structures you can draw, but only one structure that's chemically reasonable. So I've included some guidelines here for making sure your structures are reasonable. First, structures that can easily eliminate water or acid, like HX, are typically not very stable. Molecules that are almost aromatic will find a way to become aromatic. There is a big energy gain associated with aromaticity, so you want to avoid structures that are almost aromatic. Molecules with strained double or triple bonds are not stable. Forcing an alkyne into a ring structure where it cannot achieve the desired linear or 180-degree bond angles is highly unfavorable, so avoid structures like this. Avoid structures with too many OO, NO, or OX bonds. These structures do exist, but they're highly unstable and are usually explosive. Avoid too many double bonds. If you find yourself drawing a structure like this to achieve 4 degrees of unsaturation, then instead you should consider drawing an arene ring. Finally, avoid acid groups like CO2H on heteroatoms, non-carbon atoms. There's an energy gain associated with the loss of CO2 or SO2, and so these structures will also often be unstable.